Everyone, welcome to Behavioral Aspects of Cybersecurity. In this lecture, we're going to cover modeling threats. Let's start out with a quote from Sun Tzu's The Art of War. If you know the enemy and know yourself, you need not fear the result of 100 battles. If you know yourself but not the enemy, for every victory gained, you will also suffer a defeat. If you know neither the enemy nor yourself, you will succumb in every battle. From this quote, we can see how important it is to know our enemy. In this case, for our cybersecurity point of view, our enemy are cyber attackers. People are trying to gain access to our networks, maybe gain some data, but they're trying to bring harm to our networks, bring harm to our systems. So this quote is saying that we need to know who our attackers are, what they will attack, how and why. But more importantly, it's saying that we need to know ourselves. It's important to know what our system's strengths, weaknesses, and limitations are. In the last couple of weeks, we talked about the importance of also having people in our systems, people in our networks, also educated and things like that, because they could be vulnerable. All of that rolls into knowing ourselves. In this lecture, we're going to talk about how we can understand who we are, our networks, our vulnerabilities, and also our enemies through models. So we're going to be looking at how do we model our cyber threats in this lecture. So we've seen this slide and the next slide also a couple of times, especially now we're coming towards the end of this semester. But this is a great slide to show the overlap between modeling simulation, cybersecurity, and human factors. The cybersecurity part of modeling and simulation is looking at a couple of ways that we can have people better trained, better rehearsed for different kinds of cyber operations, being able to know what's better practices for our networks. That involves having cyber ranges. We've talked about this a lot. Anomaly detection, operating system modeling, and attack vector simulation. And we're going to get into a little bit more to simulation in this lecture. On the left-hand side, you see behavioral aspects of modeling simulation. So this is more the cognitive approach, the human aspect of it. So we're talking about training and performance. How do we have people inside our systems, inside our networks, better trained to understand the vulnerabilities and things like that, but from the modeling and simulation aspect of it. It's interdisciplinary because there are a lot of different people coming with a lot of different backgrounds, psychology, computer science, engineering, who are trying to solve problems that are all about different modeling and simulation. And then again, the cognitive aspect of it. How and why are people doing the things that they do? What are their thought processes? This is just generally for modeling and simulation, their behavioral aspect of it. Well, at the very bottom, you see the behavioral aspect of cybersecurity. How can we take those two things of behavioral aspects of modeling and simulation and cybersecurity for modeling and simulation and get a better understanding of why people are doing the things that they're doing to try to gain access to networks that they shouldn't have access to. So that's talking about insider threat detection, cybersecurity workforce development, training those people to know what the best practices are, attack prediction, and hacker motivation. Again, none of these are exhaustive lists, but it's rolling up everything that we've seen before, the cybersecurity aspect of modeling and simulation, the behavioral aspect of modeling and simulation, and applying it to protecting our networks to better understand the attackers, their motivations, and why they're doing what they're doing. Also, we know that there are different kinds of actors out there in the attack space, in the prevention of attack space. That's the white hat hackers, the black hat hackers trying to gain access to our systems without authorization. And then all the way to the very bottom, we have those who don't necessarily know what they're doing. They're just running scripts, those script kiddies, but they can still be a threat to our network, to our systems, because if they're running a vulnerability, if they're running a known vulnerability that we don't have a patch for, then they are as big of a threat as anybody. So the modeling aspect of it is to be able to model these different kinds of cyber actors in our system so we can get a better picture of who they are and what they do. So how do these actors conduct work is what we're going to be modeling later on, but we'll see throughout a couple of the exercises that we'll see that we'll do. It's important to understand the actors at any level in order to get a better understanding of our system. And this is another slide that we've seen before, but it's showing the different kinds of methodology that we would have to consider the escalation of a hack, of an attack to one of our systems. So again, it's going all the way from footprinting. So that's the very passive queries, simple queries that you can do, such as like a whois command on an IP, just to see who's out there, and going up again a little bit more to pinging, trying to see what kind of IP, what IPs are active on a system. Maybe if we can find do a port scan, we can see which ports are open. If ports are open, maybe they're tied to specific software. Specific software can have vulnerabilities that can lead to system hacking, that can lead to an exploit. Once those maybe vulnerabilities are detected, then the attacker can gain access and then plant their own backdoors so they can later on have access to our systems. But a lot of these are common attacks because it's a methodology that is very, very frequent in terms of attack. You start out with these passive queries all the way to having someone embedded into our network because they planted some kind of backdoor. So the question is, how do we model threats in general? And what are the questions that we need to ask in order to prepare our system and understand the kind of networks and vulnerabilities that we have for our network and our system? So what can we model? One thing that we can model is insider threats. We can also model, obviously, outsider threats, but we're going to start out with, we're going to be modeling insider threats, both intentional and unintentional varieties. So this is going back to the ASIN model in the late 80s, but also we've seen some fairly recent work in something called the theory of planned behavior. Because this is the behavioral cybersecurity course, we want to understand the psychology of someone's behavior, especially on the attack side. So this kind of model is saying that we can model someone's behavior by understanding a couple of things. The first one is understanding their attitudes towards a behavior. That is, do they think a certain behavior is acceptable? Is some type of behavior positive? Is some type of behavior going to be rewarded? Next, we have the perceived social norms. These are, is it acceptable to behave in this way? Maybe an example would be, maybe there's a disgruntled employee or an employee who feels that they aren't being compensated well. Well, they may feel that it's justified for them to do some kind of theft or something. It's socially accepted, so social norms. And the last one is perceived behavioral control. This is getting into what can be considered what is thought to be the limits of some kind of behavior. From this kind of model, this behavior model, if we can understand someone's beliefs, someone's behavior, and the norms going with the control, we will be able to hopefully predict someone's intention. And if we can understand someone's intention, we have a better chance of understanding and predicting someone's behavior. So from this model, we're trying to understand why someone does what they do. And then for cybersecurity, why is the attacker going to attack the network? If they're an insider threat, why are they doing that to an organization that they're a part of? Why are they doing it to their employer? Why are they doing it to their colleagues? Why are they doing it to the people that they're already part of, an organization? So this is for insider threat. If we can understand their behaviors, what they consider social norms, and their behavioral control, then we'd be able to predict their intention and hopefully their behavior. The very first thing we have to do when we're modeling cyber threats is answer a couple of questions. These questions will allow us to develop the types of models that we want to with a more controlled and predictable future. So the first question is, what types of targets do we want to model? Do we want to model a bank or a banking system? Do we want to model HR, human resources, a website, things like that? The next question is, how can that target get attacked? How do we model those ways? So is a system, let's go with the banking, is a banking system vulnerable to a certain kind of attack? Let's say it's a DDoS attack. How can that target get attacked? Well, maybe it's going to be DDoS, maybe it's going to be man in the middle, any kind of attack. The next question is, what types of threats do we want to model? Is it going to be an insider, outsider, natural, any kind of threat? And then what types of attacks do we want to model? Again, is it DDoS? Is it phishing? What specific kind of vulnerability and kind of attack do we want to model? And then lastly, what type of tools to use in that for our modeling? Is it going to be agent-based? Is it going to be a discrete event simulation? Is it going to be a continuous simulation? which type of simulation or what type of tool are we going to use for our modeling? And we're going to be answering these through the examples that you're going to see in the next couple of slides. So in our first example of modeling a cyber threat, we're going to go through that list of questions, at least some of them, in order to get our model started. So let's start with the first question. What type of target do we want to model? So in our first question, we're going to be modeling a nuclear power plant. And we're not going to be looking at the cybersecurity aspect of it, but we're just going to use this as an example. Later on, we'll get into a cyber example. The second question is, how can that target, our nuclear power plant, get attacked? Well, one way that a nuclear power plant can be attacked is through its cooling pumps. So how can it get attacked? Well, the cooling pumps can become damaged. The next question is, how do we want to model the attack? Well, in this example, we're going to be modeling our attack through attack trees. And if you ever used decision trees, you know pretty much the same format as what you've seen in the past. Attack trees and decision trees are very similar. So let's actually see what one looks like. So here's an attack tree. And what is an attack tree? An attack tree is a formal method to represent the decisions that take place in a system. And specifically, it's how we would represent graphically the security of a system, of a network. So we're going to be using something like this, these attack trees, in order to represent what the vulnerabilities are of one of our systems. And these kinds of objects, these kinds of structures, they roll up decisions to allow us to know whether or not our system is vulnerable or subject to an attack or something. In order to make those decisions, it has a series of actions, which we'll talk about later, but are represented in these gray squares here, and operators, these here, and OR gates, these operators here. By asking whether or not something is true and using these and or gates or operators, we're able to determine what the state of our system is. With the collection of all these decisions, we will know whether or not our nuclear power plant is physically damaged, has the cooling pumps physically damaged. So let's get into this a little bit more. The very first thing we're going to have to do is break down what and or gates are, just in case you haven't seen it before. But if you have, just bear with me while we go through this example. So and or operators. The first one is the and operator. It's a logical operator which allows us to make decisions, it's true or false decisions, based off of some input that we have. So in this case, here is our and operator, this shape here. It's going to take in multiple inputs, and each of these inputs are going to be represented as a question that rolls up to answer as yes or no, true or false, 1 or 0. So we have, in this example, we have one input, x1, another input, x0, and based off of this and operator, it's going to spit out a true or false or 1 or 0. So let's go through a very simple example that I think kind of makes sense if you've never seen these operators before. So the first example is using, again, the and operator, is it a duck? And we can take in two inputs that roll up to a yes or no, true or false answer. And the first one is x0 here, does it walk like a duck? The second one is, does it talk like a duck? And these questions will be true or false. The and operator, because it takes in these two, both of these inputs have to be true in order for its output to also be true. So x0 and x1 both have to be true in order for the output z to be true. So using this example, if it walks like a duck and if it talks like a duck, if both of those are true, then yay, it's a duck. Let's look at the next operator, the OR operator. In the OR operator, it also takes in inputs. But the difference between the and the OR operator is with OR, at least one of the inputs has to be true in order to have the output to be true. Using this duck analogy, let's look at an example. So again, we're asking a question, is it a duck? But this time we're asking, is x0 true or is x1 true? And we're changing our questions a little bit. So does it quack? Yes or no? And the second one is it a mallard, a type of duck? So if one of these questions is true based off of something that you're observing, then congratulations, it's a duck. It'll be true. But if both of these are false, the output would be false. It is not a duck. So at least one of these inputs for the OR operator has to be true, and for the AND, all of the inputs has to be true in order to get the output true. Let's see what it looks like in our attack tree and how it kind of rolls up with the logic. And I think seeing the next one kind of makes it a little bit more clear if you've never seen these logical operators before. So here's our example using the nuclear power plant non-cyber threat. We're asking whether or not the nuclear power plant was physically damaged due to its cooling pumps being damaged. At the very top of our attack tree, we have the root. The root is asking yes or no if our plant was physically damaged, was attacked. And you'll notice that underneath our root, we have different kinds of operators. Here's our gray square, which represents an action. We have an OR gate, which represents some logic. And the same thing with an AND operator, which also represents some logic. These logical operators tell us whether or not something is true or false, if a decision or a state is true or false. If we look down here at the bottom, you'll see that there's an AND operator, whether or not a sympathizer was inserted into the plant. Sympathizer could be attacking our plant. So this is just one way that we can determine whether or not our plant has some kind of compromise. So we're asking here if a sympathizer was inserted into our plant. And underneath this AND operator, you'll notice that there's a couple of actions or behaviors that would be satisfied or not. So under here, we have three. We have create a trained agent. So if somebody was trained to be an agent, someone has been applied, who has applied for employment at the plant, and whether or not that person has passed screening procedures to be an employee at the plant. All three of these conditions must be satisfied in order to have this AND operator be true, to be satisfied also, because it's an AND operator. So again, AND operators require all inputs to be true. So when I ask the question, what happens here if we decide that all these two actions were actually satisfied? We trained an agent, or a sympathizer had a trained agent who applied for employment but did not pass the screening procedure. What would happen here? Well, because not all of these actions are satisfied, are true, this would be false. This AND operator here to insert a sympathizer into the plant would not be satisfied, would not be true. So the answer in this case would be false. We can look at the same thing with the next level up. Place an authorized insider in the plant. This one is to make sure that the sympathizer was placed in the plant, and we know that this one is false if we could not pass, if that sympathizer did not pass the screening procedure. So this is an OR operator, and the OR operator, if you remember, requires that at least one of the conditions below it, the inputs below it, is true. Well, as long as this one, this blackmail or intimidate an existing employee, was satisfied, well, we'd be able to make this a true statement here and roll this up, even if we saw that this was false here because the agent did not pass the screening procedure. This condition here would be satisfied as long as this action here was true. So by rolling this up, going from a top-down approach, we can determine whether or not, if we keep going up, whether or not the physical nuclear plant was damaged because of the cooling pumps. We use these logical statements, true or false, to determine what the actual state of our overall system is. And it's a bottom-up kind of approach. So going up one step, we can take all of the inputs that we have, make some determination, and we'd be able to determine yes or no if the nuclear power plant's cooling pumps were damaged. Let's look at another example. So we're going to ask the same questions, but now look at a different condition. So the first question that we're going to ask is, what type of threat do we want to model? In this case, it will be an outsider attack, and we can ask the next question, what type of attack do we want to model? In this new example, it's an outsider threat of some kind of system that has some data, and we're going to be looking at whether or not someone is stealing personal identifiable information, PII. So in this example, there's some system, and we want to determine whether or not personal identifiable information has been compromised from an outsider. And here's another attack tree. In this case, we don't have the shapes of the operator, but the red nodes represents the OR operators, and you can see the gray ones, in this case, representing the ANDs. So everything below it has to be true for the ANDs. And for the ORs, at least one of them. So here is our root. We're asking whether or not personal identifiable information has been stolen here at our root. And because it's red, it's an OR. So at least one of these conditions below it has to be true in order for the system to be compromised. But let's roll up and let's look at some of the leaf nodes, the very bottom actions that you see down here. In order to lead to stolen PII, we would ask some questions that go with, was a key card stolen or credentials stolen? Was the home system, a user's home system hacked? Was the mail server hacked? Did someone was able to hack through the firewall? And let's look at this AND statement here for physical access to the server. Both of these conditions have to be true in order for this condition to be true. So if someone stole a physical key card to gain physical access into a system, and if they had some stolen credentials, then we can say that the physical access was compromised to the server. For this OR operator here, intercept email, at least one of these conditions that are connecting to it has to be true. So either a user's home system was compromised, or the mail server's gateway was compromised or hacked. One of these conditions would be true. As long as one of those conditions are true, then we can say that email has been intercepted. And then the last one over here was there a hack into the system? So maybe a hack took place through the mail server, maybe someone hacked through the firewall. At least one of these would be true. If one of these were true, then we know that there was a hack on the server and we roll it up. And then again, at the very top is another OR. So at least one of these conditions at this level here would need to be true in order for us to say that there's probably a compromise and personal identifiable information has been stolen. So with these attack trees, we're able to come up with a flow, almost like a decision tree, whether or not a system has been compromised, or we can map the different kinds of vulnerabilities that would lead to a compromise or some kind of attack. In addition to attack trees, we have a couple of other tools that we can use to model cyber threats. These include agent-based, continuous, and discrete event simulations. These simulations model the processes and operations of a system, whether it's your network, the software in your network, the people in your network, or your organization in general. Anything that we want to model the cybersecurity vulnerability and strength in a computerized way. What makes these simulations different than attack trees is it's automated with higher detail and complexity than we'd have in just the decision trees that we've seen with the and or operators. Typically, those attack trees would be manual, where these simulations would be automatic, and automated, where they're based off of either a game loop or a tick, where it's automatically taking in some kind of input or stimulus to model and progress the simulation. For example, in discrete event simulators, they progress the simulation through the change of different kinds of events. Each of these events would be a state that we're trying to model. For example, previously we looked at how we would have a system compromised. So a different kind of event, different kinds of events would be stolen credentials, a key card being compromised or stolen, a compromised firewall, mail server. When we can detect one of those things happening in our simulation, that would be an event. The event will then drive the simulation to move forward to the next status level, and then we can model what the response would be in that simulation. While continuous models do exist, and we're seeing an increase in simulations being used for cyber threat modeling, agent-based models and discrete event simulations need further exploration and development to really see these types of simulations be used for cyber analysis. Simulations are typically more costly to produce than attack trees, and agent-based models and discrete event simulations have a higher cost than continuous models in general. That's because understanding the subjects, the targets, the mode and plans of execution are much more expensive to understand and realize than these other types of modeling. There's also an increase in complexity for the engineering and the post-analysis as these simulations are going through than just the base of these. Ongoing IST research is developing cognitive models to understand the attackers, the responders, and the systems at a different level than what we've seen previously in order to increase the fidelity of those agent and discrete event simulations. The main goal is to understand, analyze, and predict the motivations, behaviors, and the intents of all actors and systems. For example, we talked about before the different kinds of hackers that are out there. It would be great if we understand what their behavioral patterns are so we can model those and have much more accurate predictions for our systems. Regardless of the type of model that we're using to model cyber threats, models should factor in the types of targets, vulnerabilities, threats, and attack tools that can be used to gain access to a system. In particular, attack tree helps us map out the systems, processes, and vulnerabilities graphically in a way that's pretty easy to understand. You can look at a bottom-up approach where each state is represented in our system, and using those operators that we saw before, we can determine whether or not a system is compromised. Generally, simulations go one step above. Where attack trees are generally manual, simulations are automated. They have higher resolution than attack trees, but they require much more effort to get them right. That's because of the level of detail that's needed to build these automated models to have each part of the system that we're modeling to be reflective of the actual real system that's out there. That concludes today's lecture on these types of cyber threat modeling. If you have any questions, please feel free to reach out to us. Take care.